Here are some notes dealing with Chapter 2. Okay, so the first thing we looked at in Chapter 2 was converting from degrees to radians or radians to degrees. And I give you a couple of ratios that you could multiply by, but now I'm going to show you how it makes sense, hopefully, right? Well, in the chapter, remember, 180 degrees corresponded to walking halfway around the circle, which was a distance pi radians. So the point is, pi radians is the same as 180 degrees. So this is a smart value of 1, because pi radians is the same as 180 degrees. Okay, so if I want to convert from degrees to radians, what I can think about is, okay, it's 30 degrees. The point is, I keep my units with my numbers, and I treat them like numbers. So if I have 30 degrees, and I multiply by pi radians over 180 degrees, do you see how my degrees cancel out, and I end up with what, radians? So that's why it should make sense that 30 degrees times this is 30 pi over 180, what, radians, because radians is the only thing that's left. And of course, that cleans up to be pi over 6 radians. Now this concept of treating units as numbers is used a lot in chemistry and in physics, and it has a fancy term called dimensional analysis. Okay, so if you keep your units with your numbers in your formulas and treat those just like numbers, then that's going to be a big help in figuring out whether or not you have the right formula. All right, now suppose I want to convert from radians into degrees. Well, so I start with 5 radians. What do I want down here? Radians, okay? But pi radians is the same as 180 degrees. Now my radians cancel, and I end up with degrees, and what I get is 5 times 180 over pi degrees, which is 900 over pi degrees, okay? Now, you may not know what that is, but it's a perfectly acceptable answer. Okay, so once you figure that out, here are the common angles that we talked about in Chapter 1. Pi radians, that's walking halfway around, that's 180 degrees. If I take that and divide by 2, pi over 2 radians then is half of 180, or 90. If I take the first one and divide by 3, pi over 3 radians is 60 degrees. If I take the top one, divide by 4, I get 180 divided by 4 is 45 degrees. And if I take the top one and divide by 6, I get 180 divided by 6, which is 30 degrees. So here are the common angles, and here are the radian equivalents. Okay, that then gives our common triangles the following value. 45, 45, 90 is pi over 4, pi over 4, 90, which is pi over 2, right? Recall, those are the values of the hypotenuse and the sides. The other one is pi over 6, that's 30. Pi over 3, that's 60. And pi over 2, that's 90. That's my other common triangle, right? So we're going to be working with radians from here on out. You might as well remember those angles. All right. Now, in the chapter, I talked about finding the values of sine and cosine. But the only ones I looked at were where they intersect the coordinate axes. And in fact, one example, which I'm going to repeat here, is suppose I want to figure out the cosine of pi and the sine of pi. Remember, I take a unit circle. My angle starts at the positive arm of the x-axis. And if pi is positive, which it is, I measure it counterclockwise. And what is pi? That lands me right here. Well, since I'm on the unit circle, that's a radius 1, I know that corresponds to the point -1, 0. Therefore, cosine pi is -1 and sine pi is 0. Now, let's look at another angle that doesn't intersect the coordinate axes, 5 pi over 6. Okay, so think about 5 pi over 6. By the way, 5 pi over 6 is greater than 90 degrees. You don't find too many triangles that have one of those in there. Still, there could be some. All right, so what's 5 pi over 6? Where am I on the unit circle? That's the question. Well, if I walk 5 pi over 6, I have not quite walked pi. Pi is all the way here. How short am I? The answer is I'm pi over 6 short of pi. All right, but so 5 pi over 6, there's my terminal side. I'm pi over 6 short. Now, I take this point on the unit circle on the terminal side, and wherever I am, I drop a perpendicular to the x-axis. That gives me a right triangle. And if I can figure out what these sides are of the right triangle, then I can figure out what the coordinates of that point is, by the way. This is called a reference triangle, and this is called the reference angle. Pi over 6 is the reference angle for our original angle, 5 pi over 6. All right, well, if this is pi over 6 and this is pi over 2, then guess what? It is one of my common angles. Pi over 6, pi over 2. The other one's got to be pi over 3, so I fill it in. Here's pi over 6, here's pi over 3. The hypotenuse, remember, is 1. That allows me to fill in these sides, 1/2 and the square root of 3 over 2. Well, if I know those sides, then I know where it intersects the unit circle. Okay, because the x-coordinate is this value square root of 3 over 2, except since it's in quadrant 2, it's negative. The y-coordinate is this height here, which is exactly half. So I know the coordinates of this point are minus square root of 3 over 2.5, but remember they correspond to what? Cosine of 5 pi over 6, sine of pi over 6. That tells me that cosine of 5 pi over 6 is minus root 3 over 2, and sine of 5 pi over 6 is 1/2. All right, let's look at another example, 9 pi over 4. I want to find the cosine and the sine. So 9 pi over 4 defines an angle. All right, now 9 pi over 4 is 8 pi over 4 plus pi over 4, or 2 pi over 4 plus pi over 4. So I start here, I walk, not 2 pi over 4, but 2 pi. I start here, I walk 2 pi. And then I walk another pi over 4. Okay? So my hint is to you, take out multiples of pi, and that to figure out where you are in the unit circle. All right, so what I've just said is I walk, what? 2 pi and then another pi over 4. Now, from this point where I end, terminal side, I drop a perpendicular to the arm of the x-axis. That gives me a right triangle. Now, there's my right triangle. I walked 2 pi. What was left? Pi over 4. Well, so if this is pi over 4 and this is pi over 2, I know what this angle is. It is pi over 4. which is what? Another common triangle. So it's a common triangle, pi over 4, pi over 4, pi over 2, 45, 45, 90. The hypotenuse is 1, and that allows me to fill in these two sides because it's exactly the common triangle I know. Well, once I know those sides, then the coordinates of this point are easy because the x-coordinate is just this length, square root of 2 over 2. The y-coordinate is just this length, square root of 2 over 2. But again, that corresponds to the cosine and the sine of the angle, which you will recall was 9 pi over 4. Therefore, cosine of 9 pi over 4 is root 2 over 2. Sine of 9 pi over 4 is also root 2 over 2, and I've computed the sine and the cosine. All right, the last little game we're going to play is this. Instead of giving you the angle, I'm going to give you the terminal side. Well, the terminal side is enough to figure out what that point is. All right, so let's look at this little fun thing. So find the sine of theta and the cosine of theta for an angle theta whose terminal side goes through the point minus 2, 3. So here we go. Minus 2, 3, it's up here somewhere. I take the line from that point to the origin, that defines the terminal side. Once I know the terminal side, that defines this angle here, theta. And I want to figure out the sine and the cosine of that angle. All right, so the way I play this game is I drop perpendiculars from this point down and from this point down. And I've done that in this picture here. That gives me two triangles. This triangle here and this triangle here. Guess what? Those triangles are similar. Why? Because they have the same angles. This angle's the same. They share this angle. That automatically makes these two angles the same, so they're similar. Well, if they're similar, then then one is a scaling factor of the other one. All right. Now, the outside triangle, I know this length is 3 and this length is 2. For the inside triangle, I know the hypotenuse has length 1. Why? Because it's on the unit circle. So this hypotenuse is of length 1. What's the hypotenuse of the larger triangle? Well, I have to use the Pythagorean theorem. And the Pythagorean theorem says that it is the square root of this squared add this squared. So 3 squared add 2 squared, 9 add 4 is 13. This hypotenuse here is a square root of 13. Well, so what do I multiply the square root of 13 by to get 1? And the answer is 1 over the square root of 13, right? So what's this length side? It's 3 over the square root of 13. And what is this length side? It is 2 over the square root of 13. And there I filled that in down here. So this is 3 over the square root of 13. This is 2 over the square root of 13. This point corresponds to cosine theta sine theta. But I know the coordinates of this point because what's the x? Well, it's just this value, except it's negative because it's in quadrant 2. What's the y? It's exactly this length right here. 3 over the square root of 13, that tells me. Cosine theta is minus 2 over the square root of 13. Sine theta is 3 over the square root of 13. And that is starting with just telling you where the terminal sides are. Finally, I want you to note that all sides in all triangles I will write are treated as what? positive.